This is, my drawing is supposed to be, this paper is perpendicular to the board, the arrows are going straight through it. That's the intent. And I have an area here of 4 square meters. What is the electric flux? Oh, I might be assuming things. We haven't done area vectors yet. Okay, let's talk about area vectors. Sorry, I jumped ahead. But I'm guessing none of you studied over the Christmas break. Especially the stuff that's not in the textbook. All right, so I have a surface right here. We need to somehow describe, we have this area vector. How do you, in what direction is the area of a surface?
In what direction?
This is the area of the surface.
Yeah, this is a vector, area vector, so area would be, physical, the magnitude would just be the area of the piece of paper, but it has a direction. So what is the direction of a piece of paper?
Going out from the paper?
Yeah.
Going like that way or that way?
Yeah.
Why?
Because it makes logical sense.
And that's exactly right. It makes logical sense. Because you can't really do it parallel to the paper, because why would you give preference to one direction or another? So they came up with this method of, to determine the direction of the area, they picked a vector that is perpendicular to the page. Now, a piece of paper has 2 surfaces, so the vector could be up, or it could be down, or like this, to my right or to my left, depending on how you want to do it. So the area vector, the direction of the area vector is perpendicular to the surface. Because remember, dot products care about parallel. So if my area vector is parallel to the paper, I'm going to get the maximum flux here, because my area vector is in the same direction as my electric field. So this is my area vector. Just depends on how formal we want to make it. Let's just make that the I direction. So my electric field here is 5 newtons per coulomb I hat. That's my electric field. Dot 4 square meters I hat. When you're multiplying the dot product, don't forget we end up with a scalar, and you multiply like components. They are both I hat components, so those will multiply together. Doing the fancy math, see if I get this one in my head. 20. 20 what?
Newton meters squared per coulomb.
Which for some inexplicable reason has no single word unit. It is indeed in Newton meters squared per coulomb. Oh, I think you forgot the curve.
That's okay.
Okay, I apologize. Newton meter squared per coulomb. No direction, because it is a scalar. We could have found the dot product a different way, because it is a dot product. This is also the magnitude of the electric field times the magnitude of the area times the cosine of the angle between them. Which would be 5 newtons per coulomb times 4 square meters times the cosine of 0 degrees. However, there is a second answer. What is the second answer? That would also be just as correct.
Negative.
Because the area vector is perpendicular to the surface. I have an open surface there, so it could go to the left or to the right. That would be your left and your right. So if we pick the area vector going this way, then this would be a negative here and a negative here. This would be 180 degrees. We'd end up with negative 20 meters per coulomb. And sometimes just cramming letters in doesn't quite work well. There's 180 degrees. They are both correct. On a test or a quiz, unless I specify what are the two answers, just give me one of them. Traditionally, you make the area vector the same direction as the electric field. But do be consistent, and as an example, if I take this and now I bend it, in essence, I have to treat this like two different surfaces. So my area vector is either going to be pointing out like that or in like that. Don't have it pointing to that way on this side and down on this side. So you stay on one side of the surface. And I think one of the master set problems, either have the bent surface with a constant electric field, or I have two electric fields and a flat surface. I can't remember which one. I think I did one for this group and the other one for the 252. All right, questions to hear?
So is it always close to 180, or will that like change it? Like
The 180?
Yeah.
That's 180, well, it was 0 degrees the first time we did it. It was 180 just because I had the area vector opposite the direction of the electric field. Let's do one where it's neither 0 nor 180. All right, so I've got my 5 Newton per coulomb electric field, and now I have this at a jaunty tilt of, we'll make that 30 degrees. Still 4 square meter area. And as usual, I made my angle look like a 45-degree angle, but labeled it 30 degrees. It might be a little bit nicer if I actually try to draw a 30-degree angle. So let me do that. That's probably closer to 30 degrees. And it actually goes through, just don't want to get the impression that it suddenly gets blocked. This is not X-ray vision and let it. All right, so what's the direction of the area vector? Do you want to go that way? All right, not that way. Okay. If you like it going the other way, feel free in your notes to put it the other way. There's my area vector.
T10?
It wouldn't be more than 180.
Okay, so then,
It depends on what I assume you're talking a 210-degree angle.
yeah.
I think that would make it, that would be somewhere over there.
Never mind.
All right, the important thing is, what is that angle? Because we're doing a dot product. I have this electric field going to the right, and I have this going off at that angle.
It's 120.
Plug it into this angle right here. This is theta. What is it?
120?
120?
Oh, at 92.
I don't think it is 120. No, it's not 120. Yes, it is 120.
Wait, that's 90, right? You just add the 2.
No.
Well, it's perpendicular.
Yeah, you just said 90. Yeah, you're right.
Yeah.
Sorry to have doubted you.
Gosh, I'm the teacher.
All right, so it is 5 newtons per coulomb times 4 meters squared times the cosine of 120 degrees. Which puts it at 10, I believe, negative 10 newton meters per coulomb. Biggest mistake I see students do is they see the angle 30 degrees there and they automatically go, that's theta, and they just plug it right in.
So what is the angle that you use?
So when you're doing dot products, the angle is the angle between the two vectors, and so since the electric field is going to the right and this is going perpendicular to the surface, that's the angle that we need right there.
So you just add 90 every time, right?
No, you really, I hesitate to make any generalization because it really depends upon how I give you the information.
All right.
All right. I think we're ready for the first of Maxwell's equations.
Who's next?
James Clerk Maxwell.
I'm really old then.
Well, now. He's the one who first derived the speed of light. Actually, he derived the speed of an electromagnetic wave. You'll hear a repeat of the story. And at the end, in what sometimes seems like a rare show of humility among physicists, said, because the value of the electromagnetic wave came so close to the experimental speed of light, he speculated, he said, I think that light might be an electromagnetic wave. Which turned out to be true. All right, so I have a chart here, and we'll just cleverly label it Q. I'm going to imagine a surface here, a sphere surrounding it. This right here is known as a Gaussian surface. It is not one that it's not a physical barrier. It's just you just imagine that there's this surface surrounding whatever it happens to be. Now, because this is a sphere, it's a Gaussian sphere, but they're not always spheres. The radius of this sphere is r. And what I want to know is, what is the electric flux through this surface? So the electric flux through the surface. I'm doing what is known as a pseudo-derivation. Pseudo-derivation of Gauss's law of electricity, or electrostatics, probably better. I think it's generally local electricity. As in, we're going to derive a very specific case, and then we're going to generalize it. The formula we're going to end up with actually works beyond our very limited scope here. All right, so at this point right here, what's the direction of the area vector? So Anna, you pointed that way?
That way or
All right. So here's the one slight difference between the piece of paper and a closed surface. For a closed surface, the powers that be sat down and they said, it is always outside. If it's an open surface, it could go either way, but for a closed surface, the area vector is always away, or always towards the outside. So the area vector actually is just in that direction at that point.
then you can Can you pick any direction? Since it's a sphere.
Well, I mean, you have a, because it's lighter than the bowling ball. You have, you say just pick any direction, it has to be perpendicular to the surface, that's still true. So at this point it's that way, at this point it's that way, at this point it's that way,
Okay.
at that point it's that way. It's always perpendicular to the surface, and if it's a sphere, that means it's always pointing away from the center, assuming the charge is at the center. Now, the electric field at this point right here. What is the direction of the electric field? What do we know about directions of electric field?
If it's positive, it goes.
All right, now in this case, I didn't tell you whether Q is positive or negative. So when you're doing problems like this, generic problems, you just assume Q is positive. The only repercussion is that if Q ends up being negative, then you'll end up with a negative in the equation, and it's just the opposite direction. So there's no loss in generality, just assume it's positive. So the electric field is going away from it. So the electric field at this point is going in that direction. What about at this point right here? What's the direction of the area vector? What's the direction of the electric field?
That's what you're thinking.
Disco was born. Matter of fact, no matter where you are on the surface, the area and the electric field are always in the same direction. And so my electric flux is E dot A. In reality, since we don't have a constant electric field because the direction is constantly changing, we would break this up into the sum of an infinite number of electric and area vectors. But if we add up all the electric fields and all the areas, it basically just comes down to the magnitude of the electric field times the area. What is the magnitude of the electric field at that surface?
The KQ over R squared.
It's the same distance from the charge, so it's KQ over R squared.
Yeah.
What's the area? What's the surface area of a sphere?
2/3.
It's
What was it? 4/3.
like 3/4 or 4/3.
4/3.
Pi squared.
You've confused both the formulas.
Cool.
It'd be very similar to saying that the circumference or area of a circle is 2 pi r squared.
Is it
you
cubed?
Combine two formulas. Pardon?
Is it cubed? No, it's not.
You know,
4/3 pi r cubed
Yeah,
is the
right.
volume
oh,
Oh,
and the area.
what's that?
Then
For those who've had calculus, take the derivative with respect to r.
or
He's here.
4 or 4.
4/3 pi r cubed is the volume. Take the derivative with respect to r.
4 pi. No.
Oh.
For those who haven't had calculus, sorry about that.
Say it again.
What's it?
Take the derivative.
Of
4/3
that.
pi r cubed, if you take the derivative with respect to r,
4
That's something
pi
squared.
r squared.
yes.
Yeah.
If you take the area of a vector, pi r squared, you take the derivative with respect to r, what do you get?
R squared. No, it's not.
How many have had calculus in here?
Yeah.
Pi r cube over 3.
Okay, you haven't had calculus and you're going for it?
I have had calculus. I just,
Okay.
1/2 pi r.
You multiply by 2,
Yeah,
you get
sorry.
2 pi r.
Oh, you got 2 pi r.
So the volume, take the derivative of the volume, you get the surface area, take the volume,
Oh.
take the area of the derivative, and you get the circumference.
Derivative,
That
integral,
was
same.
a longer side note than I intended.
Well,
4 pi.
All right, so now we have our electric field, k cubed over r squared times the area vector, 4 pi r squared, and lo and behold, the radius disappears. The actual radius of the sphere has absolutely no bearing on the flux. So what we're left with here is 4 pi k cubed. Now, this right here. Now, questions to here before I introduce a new symbol. All right. There is another thing that shows up a lot, known as permittivity. Permittivity is an indication that if I have a material with an electric field running through it, how is it going to react to the electric field? So I take a neutral material, expose it to an electric field, and there's going to be some reorienting of some of the atoms. And so how it reacts to it is basically what's measured in permittivity. There is something else called permittivity of free space. This is sort of, that's what the 0 down there means. So permittivity of free space. And that's sort of the smallest value that this epsilon, that permittivity will be. That's an epsilon, by the way. So if I'm finding the electric field in free space, which is what we've been doing, I haven't said it explicitly, but what we have been doing, then using K works fine. However, if I had an electric field through a medium, so I have a charge in the middle of a donut, what's the electric field in the middle of the donut? We'd have to take into account how does the donut react to the electric field? Because we talked about before that as polar molecules start to reorient themselves, we create this counter electric field, which lowers the overall electric field. So we need to generalize this slightly more because K is a specific number. And it turns out that 4 pi K, or K sub